I'd like to comment and code on a question called Lru Cache. Now, this is essentially a problem that wants us to implement something called a Lru cache, or the full form is a least recently used cache. It has a capacity that is predefined, and we can see that in the constructor. The client would actually pass capacity as an argument, and the capacity would be set. Now, generally speaking, the data structure doesn't necessarily have a resizing functionality associated with it. The main purpose of this data structure is to essentially have a data structure which can get and put entries in O of 1 average time complexity. And the whole thing about least recently used is that if the capacity is met, in which case if the capacity is exhausted, then we evict the least recently used entry to accommodate the entry that we want to essentially insert into the data structure. So the get operation puts the data into the front, because if we're essentially putting something into a data structure, then that itself makes it the most recently used, and so it warrants that that particular item should be at the very front. And every time we get something, like if we put something rather than if we're putting it, then that would make it the most recently used, and so we put it at the front. If we get something, then we've used that frequently as well. We have an operation that incorporates that entry, and so it should now deserve a spot at the front as well. So both of these are true. So most of the popular implementations on this data structure will include a hash map and a doubly linked list. And that's particularly because with a hash map, we actually have O of 1 lookup time. And so if you think about getting something in O of 1, usually that's associated with a hash map. And if you want to put something in O of 1, especially at the front, you usually think of a linked list, right? Because if you think of an array, you would have to resize the array, or not resize, but you'd have to shift all the elements in the array to a particular side, the right side, and then where that gap is, you would then put your element. And then if you wanted to do that again, you'd have to do the same thing. And usually the solution to that is to use a doubly linked list or a linked list. In our case, doubly linked list would be most efficient, and we'll see why during the implementation. Now, we're going to first include the implementation of the node. Now, it will be an implemented detail, so it's going to actually be part of the Lru Cache class, and it will have a previous reference. In C, they call it pointers and whatnot, but in Java, these are references. You can think of them as pointers. Just as doubly linked lists have, it will have a previous reference, and it will also have a next reference to sort of facilitate that doubly linked list behavior. And you will also have a key, and you'll also have a value, and this will help us help our data structure be backed by a hash map for O of 1 lookup time. Now, as you know, in any class, you have your attributes, but then in addition to that, you also have your constructor. So we pass in the attributes that we want to make available to the user into the constructor here, into the parameters of the constructor. And of course, naturally, the key that we passed in should correspond to the key that we have on the class level. And the same can be said of the value attribute. And that really concludes that in terms of the node implementation. Usually in linked lists, you see the references. In a single linked list, you just see a next reference and the value, because each node consists of a reference to the next node in line in a singly linked list. And of course, it has a sort of a subcontainer for the value that the node holds. In a doubly linked list, you'd expect to have a previous reference in addition to the next and the value, of course. But in this case here, we have a key value pair just so we can facilitate the O of 1 lookup time because we want to be backed by a hash map. Next, we're going to look into some of the attributes of the actual LRU class, and we'll move forward with some of the methods that we've been tasked with creating. So in the actual class of the LRU cache, in terms of its attributes, we're essentially going to have a head. These are Sentinel nodes. They're dummy nodes. They're not nodes with actual meaningful values, but they're going to essentially point to the real head of the list and the real tail of the list. So you can think of our, singly linked list, maybe something like this, where, we have a reference. Each of these containers, these are nodes, and they each refer, in both ways, right? One refers to the one in front of it, and then, of course, this node in front of it refers also to the back. And each of these nodes will share that property of having both of these pointers, because that's what we have. We've defined these properties in the node class, and so naturally, if these are nodes, then they share that property. But we're gonna create Sentinel nodes, right? And these are Sentinel nodes that also have the property of having a previous and a next pointer. And we're going to sandwich, so we're going to basically sandwich our list with these Sentinel nodes. So this will sort of be the tail. This will sort of be the head. And the head will essentially point to, the first node, the first meaningful node. And the tail will also point to the first meaningful, sort of tail, right? And what this allows us to do is, if we want to insert something into the list, then we can make use of this Sentinel node to actually do that in O of 1 time. And remember, the insertion, or what they call put, the put operation will actually be always at the front, right? Because if we're putting something, technically it's the most frequently used, and so it deserves to be at the very front of the list, right? And it will naturally kick things back and maintain a sort of a rank. And so naturally, in order to facilitate that, we'll have a head node, and remember, our constructor actually takes in a key, and it also takes in a value. Now, for these Sentinel nodes, we can actually have a key and value of 0, or you can say -1 as well. And of course, we'll also have a tail, as we spoke about, where we will have, again, this will be 0, 0 as well. And then we spoke of underpinning our class with a hash map. Now, the hash map would have to be a global variable because it will be accessed throughout these methods. It will map an integer to a node. So you're going to pass in an integer, which will then give you access to the node. And of course, this is a hash map here. So we have that. Now, there will also be a capacity associated with the data structure. And of course, we know that if this capacity, if this capacity is met, if it is exhausted, then we would want to abide by the cache eviction policy, which is, of course, to evict the least recently used and accommodate what we want to enter at the front. And in the constructor, several times there are questions about, which parameters to pass, right? Well, you only pass the ones which are meaningful to the user, but you still want to put default values for things that should have default values in the constructor. So every time this is triggered, you have sort of a set of default values. Now, the capacity that was passed in in the parameter should be associated with the capacity that is passed in on the class level, and the same can be said well, not, yeah, so we're only passing in the capacity. Now, here's where we begin to write default values. So the head dot next will equal the tail, and the tail, the previous of the tail will essentially point to the head. So what you can imagine is the head of the, the Sentinel node, this node, points directly to the tail, and the tail, its previous pointer will point directly to the head. And this is because it's a doubly linked list. And if there are no elements, then they both should be pointing to each other, right? And so again, there's a multi-purpose thing when the constructor is involved. The first is that, when you pass in an argument, you want to think about, okay, this argument, like, why didn't I pass in, head and tail and whatnot? Well, those arguments shouldn't necessarily be made available to the user, right? And yet, despite that fact, there should still be attributes which should have default values, right? And so this is basically how I pick and choose what should be a part of, the parameter, and what shouldn't, and what should get defaulted, right? Now we're going to move on to the get operation, and the get operation accommodates a key, which would ideally return the node. So there's a check here, and the first check is, are we trying to get a key that is valid? Does it already exist? So let me go ahead and write the logic for that. And again, since we want to know if we're trying to get something which already exists. Now, think about it. If this data structure was underpinned by an array, then we would have to traverse the entire array in O of n time in linear time in order to judge whether or not whether or not the data structure that we were underpinned by contains that item. So we would have to traverse, and we would have to say, okay, it does contain it. So that would be an expensive process, and we want O of 1 time. And so that's why a hash map is so convenient in the context of an Lru cache. So we ask, is there a key that corresponds to what the user passed in? And if there is, then we can perform the logic that would correspond with being able to accommodate the functionality that we want, or we can return -1. Now, if there is a value that matches if the key is in the map, then we know the value that we want, which is associated with that key, is also in the map, of course. And so we're getting a particular value, and so naturally we want to return that value, but we also want to move that node to the sort of to the top or to the front. So what's going to happen is we're going to create a node, and we're going to call this data, and then we're going to get. So what this line does is we've created a node, it's called data, and we're going to store it. We're getting the node that is associated with this key and storing it in data, right? Or we can call this, we can call this retrieved, right? So the retrieved node, or the retrieved node will essentially have a node within it that matches the key. So we've went to the map, we've gotten the key, and we've stored it in this node called retrieved. Now, this is so that later on we can say retrieved dot value. We can say return retrieved dot value. And what this would do for us is it would return the node value that is associated with that key. But of course, doing that in and of itself achieves one of the objectives we were talking about, which is to get the value associated at the key in O of 1 time. We've done that. But the other goal was, of course, now that we've gotten we've touched a value that was somewhere in the ranking of our data structure. That value should now move to the front of the data structure, right? So we actually have to, play around with our doubly linked list and try and see what we can do in order to get this element that we have just accessed to get this element to the front, because now it's our most recently used, right? It is not our least recently used anymore. I don't think it ever was. I mean, if the key doesn't correspond to the last item in the data structure, it was never the least recently used. But nonetheless, it had a ranking that wasn't the first, and so we want to move it to the front. So basically, what we can do is we can say, okay, well, we're going to remove. We are essentially going to remove that node. So we're going to remove retrieved from the linked list, and then we're going to insert that retrieved node into the linked list back, right? So this is, removing it from the list. So I'm just going to remove that node, and then I'm going to put it at the front. And these aren't methods that I have defined, that I have defined yet. They aren't methods I've defined. But that's what this will do. So remove will remove a node, insert will retrieve a node, right? And of course, after that, we can just return retrieve.value, which again meets that objective that we were talking about before. So that's the implementation for the get method here. So let's take a look at the put operation. We've passed in a key, we've passed in a value. So naturally, our job is to essentially put a new node, right? I mean, we've passed in parameters that correspond to, would correspond to a node, right? A key and a value. We know that our nodes have these attributes. And we want to put this into our data structure, right? Now, the first thing that would really make sense is, okay, well, can we put it successfully without any problems? The edge case is that, is our capacity exceeded, right? You don't want to exceed the capacity. So if the capacity is exceeded, then we want to, this is where the least recently used, the cache eviction policy comes in. We want to evict the least recently used and then accommodate this node that we would want to insert. We would want to accommodate that, and we would want to put that at the front. But of course, we want to evict the least recently used, which is the item at the very back. And so in order to do that, we're going to first check, okay, well, if, and you can actually delegate this operation to check if a capacity is full. You could have that as another method. But if the capacity is equal to the map.size, so what this does is, it checks, all right, well, the capacity that the user passed in, let's say 5, if we have 5 nodes in our map, then, that corresponds to, the maximum capacity. So if it is equal, then what we want to do is we want to remove the least recently used. So remove, the least recently used. And what this is going to, so what we're going to do is we're just going to get our remove function again, and we're going to remove the tail dot prev. Now, remember what I said about tail. Tail is a Sentinel node, right? It isn't necessarily it isn't the actual node at the end, right? It isn't a meaningful node with a value and so on and so. I mean, our Sentinel node at the end is just pointing to prev. So when we remove tail.prev, we're removing the last node, right? And so that's essentially how that's underpinned. So don't get confused that we're removing tail.prev. We're removing the second to last node. We're not removing the second to last node. We're removing the last meaningful node. Prev is just a Sentinel node that's pointing to the last node. And so effectively, if you were to do tail.prev, prev refers to the last node, you remove that node. And that's really the edge case. Otherwise, what we were doing before is we're just inserting a new node, really, and you could go about this by creating a new node and then doing an insert. You could say, node, node, let's say new, or you can't use new, it's a reserved keyword, but node n1 is equal to new node, and you can pass in what they wanted, key and value, and then you can just say insert your n1, right? Or of course, what you could have done is, you could have said, just pass in insert and then instantiate the object in here and then just do key value, right? This would also be a valid way of doing that. Now we've taken into account, one edge case, right? But the thing is, what if the key already exists, right? What if the node is already exists, right? Then we're duplicating items. And so I think that what we would want to do in this case is, let's see here. It doesn't make sense to have duplicates. So what we're going to do is we're just going to say, if your map contains contains the key that they've passed in, then before doing all of this logic, we're just going to remove that node, right? So we're just going to remove the node that corresponds to this key. So you can say map.get key, right? So just remove it, and then you can continue operations as we were doing before, right? It really isn't an issue. And everything else stays the same, right? So now really, the only thing we'd really have to do is implement the remove operation, and of course we would want to implement the insert operation, right? And when you remove, what are we removing? We're removing a node, right? So you're gonna pass in the node that you want to remove, and then you're also going to pass in over here in the insert, you're going to, this is a node you want to insert, right? And so, we'll look into the implementation of both of these functions here, or methods rather. Let's talk a bit about how we're actually going to remove a node. And basically what we're doing is so we're not returning anything, and we're passing in the node that we want to remove. So first we actually remove it from the mapping, right? So we take its key that allows us to remove, the remove API takes in a key and it actually removes, of course, the key, and it, of course, removes the value from the map. So we can imagine a doubly linked list like this, where these are sort of the Sentinel nodes. And, we remove node of that key. So node, we access the key the entry we want to remove in the map by saying node.key. So we'll say that the key is 4. We've passed in n2 as a parameter, and n2 has a key of 4. And so, we go to the map and we say, okay, well, we're going to remove this instance, right? And naturally what you'd expect is that it's removed from the map. And now we actually want to go through the deletion process, right? So this isn't actually a recursive function. We're not calling ourselves here. We're just calling an API on map, and that's called remove. This also happens to be called remove. And so what's going to happen now is, we're going to say, okay, well, this node, right, the node we've passed in, it's previous. So it's previous. Now we're referring to this node. So let me make this a little more clear. This node's previous. So now we're on this node. This node's previous, which is this node here, it's .next. So this .next pointer should actually be pointing to what? Node.next, right? So let me go through that again. This node's previous, so now we have a handle on this, its .next should be pointing to this node's .next. So that's what this line expresses. The node's previous is .next, so this node's previous is .next should be pointing to node.next, and that's how we've overridden the first link here. And what you'd expect for the next step is, okay, well, this node's now we've undone that. This node's next pointer, okay, what we want, the main intention is to take this guy here and point it here, right? This node's next pointer, which is referring now this node now, it's next. This guy's next, so this guy has a next, it's this, and this guy's previous should be pointing to this guy's previous, right? And so effectively what you've done now is you've done this, okay? And you know that essentially would override it. So this node's because it doesn't have a next. This node's let's back up for a second. So this node's next, this guy's previous should be pointing to that guy there. And that's how we've essentially removed that node. So node.prev.next should be pointing to node.next. And node.next.prev should be pointing to node.prev. And so that would effectively remove the node. And this node in the middle would be garbage collected. Okay. And there you have it, right? Because N3 isn't pointing to this guy as its previous, and N1 isn't pointing to this node's next as its front. So, it gets overridden and garbage collected. So this is the implementation here. So, if we go to what we were coding, we remove it from the map, and we just access the key value to do that. And we would basically just want to say that node.prev, right? Its previous's next pointer should essentially just be node.next, and the next guy's previous pointer should be pointing to node.prev, okay? For the same reason that we explained before. Let's go ahead and take a look at the okay, this is actually the insert here. So we actually want to put that in remove, okay? And now we'll look at the insert. Let's take a look at the insert functionality here. Essentially, we're inserting a node, so we want to essentially register a valid mapping. So we do map.put. We put the key of the node, and of course we put the node itself into the mapping. And this is actually the logic that pertains to the doubly linked list. So we've introduced a node, right? We'll call this and ideally we would want it here, right, where N1 is, and that's particularly because if we're inserting, the insert operation, or it is essentially to be it is essentially so the insert operation is always going to put the item in the beginning, right? Because in our LRU philosophy, sort of, if we're putting something, it is by default the most frequently used, so it should be at the front. So this is, let's say, n, okay. We'll call this n naught. Now its next pointer should point to head.next. Remember, this is the head. Now this isn't a valid, meaningful head, it's a Sentinel node, but saying n naught should be pointing to head.next is effectively just saying that n naught should be pointing to the head, since head.next actually refers to the real meaningful head of the list for all practical purposes. So for all practical purposes, n1 is actually the real head, and this head here is just a Sentinel node that allows reference to the head. And it's for these types of operations that this was useful. So we essentially we've done the mapping part, and now we just say, okay, well, n naughts, this node's next value will point to head.next, so it's actually pointing here, okay? And we know that, it also has a previous pointer. We haven't done anything with that yet, but now head.next.prev. So this guy, its previous pointer, it has also a previous pointer. Its previous pointer should be pointing to n naught. Okay, so its previous pointer will point to the node in question. Okay. Will point to the node. Okay, head.next. Okay, actually, that's actually not the intention there. Head.next, this previous, it should be pointing to n naught, right? Because remember what we want. We want n1 here, and we want the previous to be n naught. Okay, so first making sure that this guy has a handle on n1. And then we'll make that reciprocal to make sure that its previous points to n naught. So we'll say head.next, it's head.next. So head.next, now we're on this node, its previous will point to n naught. Okay. So effectively what we've done is we've brought it like this. Okay. And now you can probably see that everything is complete as we want it, except the Sentinel node isn't necessarily behind n naught, is it? So our job is to take its hand, and this head, the Sentinel node, should point to n naught. So its head.next should actually be node, right? Or so it should actually point like this here. And naturally, its node's previous should be pointing to the head. Okay, so as you can see, we've achieved our objective here. We have our head, and the head.next is n naught. Okay, n naught's previous is pointing to the head, the Sentinel node, and n1 is another node in line, and its previous is pointing to n naught, and n naught's next is pointing to n1, and so this is a valid operation here that allows us to achieve what we want. So we come to the insert method, and we basically repeat this logic. So we're going to first put the node.key, and of course we're going to put the key, and we're also going to put the node itself. That's the mapping, if you remember up here, integer and node. And of course, now the next pointer for the node should be pointing to head.next, and head.next.prev, which is the current head, which is this guy here. Head.next.prev should be pointing to the node in question, right? The node that the user passed in. So head.next.prev should be pointing to the node. And then head.next should be pointing to the node itself, right? Because we want that to be in the absolute front as a Sentinel node. And then, of course, the node's prev should be pointing to the head, because if it is all the way in the front, then the node we've entered, its previous should be the Sentinel node. And so that's essentially the idea. You can see this solution is a valid solution to implementing this type of data structure. Another point could be that the description said to add the key value pair into the cache. So each node should have that key and that value. And these descriptions are very descriptive. So basically this mentions the constructor, and it says that it will accept the capacity. So we'll have the user accept, we'll have the client accept the capacity, and the get will just take in a key of type integer, which is why we had our mapping of integer. We're just going to put the key and the value. So the putting would correspond to let's see here. The putting would just correspond to just taking the key and the value and then having it registered as attributes of the node class. And this is probably the most important, but when you put it, and so you update the value of the key if the key exists. So I think what we've done is we've removed the key altogether. Otherwise, we'll add a key value pair to the cache. And if the number of keys exceed the capacity from this operation, evict the least recently used. And these are both O of 1 operations. If we look at the get operation, right? I mean, we aren't doing any, linear searches of any kind. We're backed by a hash map. And even these methods here, if we go to these methods, these are all, there are no traversals involved with, removing. And the same thing could be said for the insertion process. There are no traversals involved with insertion. These are both O of 1 methods. And so naturally, if the entire method for the putting operation consists of O of 1 operations, then we have O of 1 altogether. The same thing can be said for get. I think that's what we were originally talking about, but the same thing could be said for put as well.